Welcome to this video. Today I'm going to talk about Isaac Newton's three laws of motion. The three laws of motion are all about forces and how they affect objects. Here we have Isaac Newton. He was alive from 1642 into the 1700s, so a very long time ago. So let's start with Newton's first law. Objects have inertia. But what does that mean? So that could mean that an object at rest will stay at rest, or an object that's in motion will stay in motion, unless acted on by an external unbalanced force. So we kind of have three different things going on here, so let's break them down piece by piece. So here we have Happy Gilmore who put a golf ball and came up a little bit short, didn't get it there all the way to the hole, and it came to a stop. Once the golf ball came to a stop, it doesn't spontaneously start moving again. It won't just all of a sudden fall into the hole. It has to actually have an external force acted on it in order for it to move again. All of Happy Gilmore's encouraging words here are not going to do anything in terms of making the golf ball move any further. The second part here is that an object in motion will stay in motion. Here we have on top we have our Futurama character flying through space, and he'll just keep flying through space forever because he's just continuously moving. He's in motion and he wants to stay in motion. On the bottom here we have two cherries with water droplets on them. So when the cherries collide, the cherries come to a stop because they hit each other. However, the water droplets are still moving, so they keep on moving even though the cherries stop because they have the ability to fly off the cherries and keep going in motion. The third part is that if we have an external force, then motion can come to a stop. So on the top here, we have our stereo flying in and hitting this guy right in the face. So the stereo wants to keep moving. It would keep moving forever. However, this guy's face puts a force on the stereo and causes it to stop. Similarly, on the bottom, we have a ball that's being thrown to this cute little puppy. When the puppy catches the ball, he's exerting a force on the ball and causing that ball to stop moving. So that is Newton's first law. Newton's second law is that the net force of an object is equal to the object's mass times acceleration. Again, that's the net force, the force on the whole system, is equal to the mass times the acceleration. So let's talk about Newton's second law a little bit. When we strike an object using twice the amount of net force, that results in twice the acceleration. So our animation here, we have a guy who first hits with a hammer and the ball goes up only a little bit. Then if he strikes with twice the amount of force, there's going to be twice the amount of acceleration, so it's going to go much, much higher. Another way of thinking about it, let's think about mass. So if an object has twice the mass, it results in half the acceleration. So here in the animation, we have a bowling ball, which has much more mass than a balloon. So when it's kicked by this rotating foot here, the bowling ball just has only a little bit of acceleration, whereas the balloon flies off. All right, so let's do a practice problem with Newton's second law. Frank and Bill here, the construction workers, each apply a force of 80 newtons to a wooden crate which has a mass of 40 kilograms. How much acceleration will the crate experience? So we have Frank and Bill, each of them are putting 80 newtons on the crate. One is pulling it forward to the right and one is pushing it to the right. So both forces are acting to the right here with 80 newtons. We rewrite Newton's second law of motion once again and know that the net force is equal to mass times acceleration. We can use our triangle here to solve for acceleration, or we could use simple algebra, divide both sides by mass to get our equation of force net divided by m is equal to a. We now have acceleration all on its own, so we can use the numbers that are given in the problem. Our net force, we add up all our forces, both are in the positive right direction, so we do 80 plus 80 for our net force, and our mass is 40, so we divide by 40. That leaves us with 160 divided by 40, which is 4 meters per second squared. That is the acceleration of this crate due to the forces that Frank and Bill are both applying to the object. So Newton's third law, our last law here, is that for every action, there's an equal and opposite reaction. So this is the kind of the classic example. When someone pushes against a wall, you might think that the only force at play there is the man pushing on the wall. However, because the man is pushing against the wall and doesn't fall over, the wall must also then be pushing against on him with the exact same force in the opposite direction. So let's take a look at a couple other examples. Here we have a couple of our characters from Brooklyn Nine-Nine who are using fire extinguishers to accelerate themselves on some chairs. So we have a similar experience where there's a force being applied. However, there's no wall there pushing against on it, so it moves in the opposite direction. Here's another example where we have a person firing a pistol. In this case, there is an extreme amount of force which the pistol applies onto the bullet. There also has to be some reaction force, also known as recoil when you're using a firearm. In this case, it's an extremely high force, and the person actually loses complete control of the gun, and it flies back at them. That's kind of scary. And this one's kind of funny. We have people getting out of a boat, and when they kick off the boat, the opposite reaction force is in the other direction, which causes the boat to move away. Unfortunately, this lady on the end there falls into the water. And then our final example here, we have our Giants player swinging and making contact with the ball. We'll notice that as the bat is swung, it hits the ball. And at that exact moment, the bat is exerting some huge force on the ball, but the ball is also exerting some huge force back onto the bat. You'll notice that the bat is moving relatively quickly at the beginning and then slows down immediately as soon as the ball strikes it. So here's a question. How does a rocket overcome its inertia and launch itself away from Earth's gravity? Well, let's first think about Newton's first law, right? We talked about inertia and how objects at rest want to stay at rest. Well, of course, when a rocket is set up and the astronauts are getting in, the rocket is, of course, not moving, so it's at rest. The rocket wants to remain at rest because it has some extremely high mass. It is very hard to move this object. So what does it need to do in order to launch itself away from Earth's gravity? Well, it needs to exert an extremely high net force. There needs to be a really high net force that allows it to overcome this inertia in order for it to blast off towards space. And these are Newton's 3 laws. They're now 3 laws smarter. This is awesome. This is our great introduction to Newton's 3 laws of motion. We're going to move forward and use these in our class.